Year 13, Functions Lesson 1. This is an introduction to functions, and we're going to have a look at the language and the notation of functions. Before we start talking about functions, we're going to talk about a slightly broader concept, which is the idea of a mapping. We can think of a mapping as a rule which allows us to travel from an input to an output. The input is sometimes also referred to as the object, and under the mapping that takes place, the object is transformed into the image. This is language that you have heard before when studying transformations. So let's look at a very simple example. I'm going to pick a mapping, which is the rule multiplied by 2. I'm going to choose some input values, which are 1, 2, and 3, and we're going to map these using the rule multiplied by 2. So very, very simply, 1 is mapped to 2, 2 is mapped to 4, and 3 is mapped to 6. If we want to generalise, we can start with x, and this is then mapped to 2x. Now, our set of input values is called the domain, and our set of output values is called the range. So for this particular example, these values here form my domain, and these values here form the range. We're now going to investigate 4 different mappings. Example A, the mapping takes us from x to 2x plus 5, which means the rule is multiplied by 2 and then add 5. I'm going to choose the numbers that are in my domain. I'm going to choose -2, -1, 0, 1, and 2. And we're going to map those using the rule x is mapped onto 2x plus 5. Basically, double your input and add 5. And of course, this is a very simple calculation. We end up with the following output values. And you can see very clearly that each input is mapped directly onto a single output like this. We will see something slightly different in each of these 4 examples. So, in the second example, the mapping is x is mapped onto x squared. So essentially the rule is square your input to generate your output. I'm going to choose the following input values: -2, -1, 0, 1, and 2. And when we apply the rule to each of these, we notice, of course, that both -2 and 2 square to become 4, -1 and 1 both square to become 1, and 0 squared is 0. So we're going to draw in the mapping paths like this. Now the next mapping, x is mapped to the positive and the negative root of itself. So x maps to plus or minus root x. So essentially square root the number that's in your input and make sure you include the negative and the positive root. So my inputs are going to be 4, 1, and 0. So of course 4 square roots to give us 2 and -2. 1 maps to 1 and -1, and of course 0 simply maps to 0. So again, we'll draw in the paths. This time, you'll notice that some of the inputs map to more than one output. Almost the opposite of what happened last time in example B. And in our last mapping, slightly more complex example, The rule is x is mapped to plus or minus the square root of 25 take away x squared. So the input items in the domain are going to be as follows: 0, 3, -3, 4, -4, 5 and -5. Now, when we input these values into this mapping or this rule, we generate the following output values, and you can check this yourself. Remember, both positive and negative roots are being included. So let's draw on the paths. So 0 is mapped to 5 and to -5. 3 is mapped to 4 and to -4. And -3 is also mapped to 4 and -4. 4 is mapped to 3 and -3, as is -4. And then 5 is mapped to 0, as is -5. So we have quite a complex pattern here in that some of the inputs map to multiple outputs which are shared by other different input values as well. Here you can see the examples that we have just completed, and in thinking about this, you will hopefully have noticed that there are 4 different types of mapping, each represented by the 4 examples that we did. The first example, part A, x maps to 2x plus 5, this is what we would call a one-to-one mapping. For every input, there is only exactly one output, so it's called one-to-one. The second example, in this case, sometimes some of the inputs mapped to the same output. So this is an example of what we would call a many-to-one mapping. The opposite way round for part C, each input, or some of the inputs, could map to more than one output. So for example, 4 mapped to 2 and -2, whereas in example B, both -2 and 2 map to 4. So this is the other way around. It's called one-to-many mapping. And then in the last example, we had, for instance, 3 mapping to 4 and -4, and then -3 also mapping to 4 and -4. So the most complex of all, this is called a many-to-many mapping. So we can see listed here the 4 different types of mapping: one-to-one, many-to-one, one-to-many, and many-to-many. Now, a function is very, very specifically defined as a mapping that is either one-to-one or many-to-one, i.e., for every input, there can only be one output. So you have examples like x mapping to 2x plus 5, where you can see that each individual value only mapped to one output, or you can have examples like x mapping to x squared, where it's absolutely fine for -2 and 2 both to map to 4, because we still satisfy the rule that each individual input only has one output. It does not matter that the output can be created from multiple inputs. So the only types of mapping that qualify as functions are one-to-one and many-to-one mappings. So having established what a function is, it is a mapping which can either be one-to-one or many-to-one, i.e. for every input there can only be one possible output, we're going to have a look at some of the notation that we can use to describe functions. Some of this you will already have seen before. So a very common way of expressing a function is to simply use y equals. So y equals x squared. This is a function. Your input is x and your output is y, and you can think of that as a pair of coordinates. We can also write f of x, f for function, although other letters can also be used as well, equals x squared. That's another way in which we could write or express a function, which you've seen before. And the third way, which you may not have seen before, is a little bit more formal. We write f is the function such that x is mapped onto x squared. And this notation here with the colon and the arrow with a strange shape, that is really important in terms of writing out a function. Now, when we define a function, we must provide some information on something called the domain of that function. Let's have a look at an example. So I'm going to define the function f of x equals 2x plus 1. Now, the domain tells me the set of possible x values that can be inputted into the function. Now, I'm going to allow any x value I want to be inputted into this function. So I would then write x is an element of the set of real numbers. And this is an example of set notation, and we'll be going into a little bit more detail about this later on. X is an element of the set of real numbers. It basically means x can be any number that, within our knowledge so far, we would allow. And this is called the domain. The set of values of x that can be inputted into the function. And in this particular example, we're saying x is any real number. We'll be talking about the concept of real numbers in a little bit more detail later on. So the domain refers to the x-axis and what we're allowing on the x-axis. So we're going to sketch our function now on this set of axes. So y equals 2x plus 1 would very, very simply look like this, with a y-intercept there. Now, the range this time, this refers to the set of possible y values that can be generated from this particular domain. So if we're allowing any x value to be inputted into the function y equals 2x plus 1, which is a simple straight line, then any possible y value can also be generated. So our range would be expressed as this. We can write down that y is any real number. Or, if we want to, we could say f of x is any real number. So the range is always expressed in terms of y or f of x, and the range specifically refers to the y-axis, or the set of y values that are possible. Let's have a look at a slightly different example. This time my function is f of x equals 2x plus 1. X will still be a real number, but I'm going to restrict this to saying x can only be greater than or equal to 3. So this piece of information that follows the definition of your function will be your domain. Now, let's think about what our range is going to look like, and let's think about what our function is going to look like. So the domain, again, always refers to the x-axis and which values are allowed there. We are only allowing an x value of 3 or above. So if we find 3 on the x-axis, if we input that into the function, f of 3 will equal 2 multiplied by 3 plus 1, which equals 7. So that generates a y value of 7. So our function will look a little bit like this, a portion of a straight line. I'm allowing the point 3, 7, so I'll draw in a filled circle there. Let's label our axes as well. So remember, the range is the set of possible y values, so we're referring to our y-axis for the range, and of course we're only allowing y values which are 7 or above. So to write down my range, I would say y is a real number, but y must be greater than or equal to 7. So to summarise, the domain is always expressed in terms of x. The range is always expressed in terms of y or f of x. If you are finding the range of a function, you need to sketch its graph and find out which y values are allowed. You're going to have a go at some examples. In each case, you need to sketch each function for the given domain and find its range in terms of y or f of x. You'll notice that sometimes we reference x as any real number, sometimes we don't, but you can usually assume that that is the case. So for example, in the first question, we haven't actually included the fact that x is a real number, but it doesn't really make any difference. Focus on the fact that you're given this piece of information. The same in some of the other examples later on as well. So let's have a look at the answers to these examples. So we're going to sketch some graphs. The first example, the graph is y equals x squared, but we're restricted to starting at an x value of 1, which of course matches a y value of 1. We're allowing the point 1, 1, so we'll shade it in as a closed circle, and we'll simply draw in part of the parabola. So the range is y is greater than or equal to 1. Or f of x is greater than or equal to 1. You can also say y is a real number as well, if you wish. Example number 2, we have another quadratic function, f of x equals x squared plus 4x plus 1, and it's defined across the full set of real numbers, so we can have any x value we want. This particular quadratic function doesn't factorise, but we can complete the square to give us some more information. And this tells us that it will indeed have a minimum point, its vertex, at the coordinates -2, -3. So when we sketch the function, we can put in place the minimum point here and sketch in our parabola. Now to find the range, we look at the possible y values, and the minimum y value is -3. We can have any y value above this, so our range is y is greater than or equal to -3. Again, you could also have f of x is greater than or equal to -3. Example 3, f of x equals 4 take away 3x, a simple straight line, and x has got to be greater than or equal to -2. So if we sketch out some axes and we mark on the point x equals -2, I'm going to substitute that into f of x and find out what f of -2 is equal to. And it's equal to 10, which means we're including this point here. If we weren't, it would be an open circle rather than a closed circle. And then the graph, which of course has a negative gradient crossing the y-axis at a point 0,4, then looks like that. Now the range of the function is that y can be 10 or below, so y is less than or equal to 10. Example 4, f of x equals sine x. So we should all know the shape of the sine function. And we can sketch its graph between 0 and 180. And of course, becomes very clear straight away that our range of possible y values is that y can be between 0 and 1 inclusive. Last example, f of x equals 1 over x. Now this has quite an interesting domain, if you notice here. We're allowing x to be any real number, but we have to rule out the number 0 because, of course, 1 divided by 0 is undefined. Again, we've seen this function before, so we should recognise the shape of it. It looks like this. And the range of y values, well, if you look at the axes, the y-axis in particular, you can have any y value you want apart from this value here at 0. So our range is y can be any real number excluding 0, so y cannot be equal to 0. So earlier on we saw this letter here, an R with a line in it, which refers to the set of real numbers. There are other types of number system as well, and we're going to look at some of the symbols for these. The most general or broad-based number system that you can think of is the set of complex numbers, which includes every possible number that you can think of. Now, students who study further maths will go and look at these in much more detail, but to all intents and purposes, every single number that we can think of falls under this broad category of C for complex numbers. Those of you who might be interested in reading a little bit more about it might be interested to read a little bit more about the square root of -1, which is something called an imaginary number. It's written as I, and you can have positive imaginary numbers and negative imaginary numbers, and they fall in this very broad-based number system. Now, much more familiar to us is a group or a subgroup within this category, which is called the set of real numbers, and it's denoted by this letter R. So it falls within the category of complex numbers. Now, real numbers can include negative integers, positive integers, decimal values, 0, fractional values. It can include irrational numbers like pi and the square root of 2, and more complex irrational numbers like that. So all of the numbers that we deal with on a day-to-day basis fall under the category of real numbers, denoted by the letter R. Now, sitting within this category, we have what we call rational numbers, and you have come across this concept before. Rational numbers are denoted by the letter Q with a line like that, and they refer to any number which can be expressed as a fraction of the form a over b, where a and b are both integers. So, any integer, negative or positive, is a rational number. Any finite decimal, i.e. any terminating decimal, is a rational number. 0 is a rational number because it can be written as 0 over 5, for instance. So any fraction, any exact fraction like 5 1/3 or 7/10, etc., they can be written as fractions in the form a over b. Any integer, positive or negative, and any recurring decimal. So for instance, 0.3 recurring. These all classify as rational numbers. They're all also real numbers as well, but they're a particular group that form within or under the umbrella of real numbers. They're a smaller subgroup of numbers. Now, within the concept of rational numbers, we then come on to the integers, which are denoted by the letter Z, like that. And of course, integers can be positive or negative, and they can also include 0. So we have our set of integers. And within the integers, we then have another set of numbers, which is referred to as the set of natural numbers, sometimes also called the counting numbers, and they refer specifically to the positive integers 1, 2, 3, etc., so excluding the number 0. The positive integers can also be referred to as a Z with a little plus sign next to it, or a negative sign if you wanted the negative integers. It is really important that you know this terminology, that you know these symbols, and in particular the symbols for real numbers and integers you will come across very frequently when you're working with functions.